So I'm just going to come out and say it. Laundry laps are stupid. So in this presentation, I'll subject you to a mini rant about laundry laps and why this absolutely matters. Then I'll give you an objectively perfect solution to the problem. I'll present 3 materials for consideration to use in this solution and evaluate their properties. Specifically, I'll talk about atomic structure, elastic modulus, and beam deflection. And once you've walked with me on that journey, I'll bring it home with a diagram that shows just how different materials can be and just how dumb I can be. So let's get to it. How far is your closet from your laundry area? Maybe it's in the basement, like mine. And maybe the way your house is structured, your closets don't live on the first floor. They're on the second floor. And God forbid you've got more than one load to do. So now you're going and doing laundry laps. You go back down just to go back up again. And it's infuriating. The industrial engineer part of my brain hates how inefficient this is. Why do we store our clothing so flippin' far away from where it needs to be washed? This is a thing that must be done in perpetuity that is seemingly specifically designed to be as inefficient as possible. Why aren't homes designed so these rooms can be closer? What, we're worried about water problems? We can build crazy high skyscrapers because we have tuned mass dampers to literally minimize the amount of sway it experiences during an earthquake. So water damage prevention on the second floor of a residential house is not an impossible task. Okay, thank you for coming to my TED Talk. Moving on. So what if it wasn't that far? What if your laundry area and closet were the same room? Like mine. This is my laundry room and my closet. No laundry laps for me. And this is how I did it. This is the solution. You throw some boards up on the rafters and put some pipe through them, and bam, you got yourself some clothing rods. Though, in my case, there's currently also a problem. You see that? Here, maybe this helps. Well, yeah, that. Lots of deflection. So it turns out that not all rods are created equal. To better investigate how unequal they are, I'm going to look at 3 material options for expanding my closet: steel, PVC plumbing pipe, and PVC electrical conduit. I'll be evaluating them based on 2 material characteristic relationships: atomic structure and elastic modulus, then elastic modulus with deflection. But ultimately, I'm answering the question of whether I'm going to return what I already bought or if I can just keep it and not worry about it. So let's start with atomic structure. Atomic structure is a materials blueprint. Here we're just going to talk about crystalline and amorphous structures. Steel's atoms sit in a tight, repeating lattice of strong metallic bonds. That's the crystalline structure. Because slip can only occur on specific packed planes, the lattice resists distortion until high stress builds. Any flaw then magnifies that stress. Once dislocations start moving, permanent deformation begins, but visible deflection remains small. When the fracture toughness limit is reached, a crack races through those same planes, so failure happens suddenly with almost no sag. Our takeaway here is that the dense metallic bonding within a highly ordered lattice is what gives us that high resistance to deformation, which, in turn, gives it that high elastic modulus we'll talk about in a minute. Now, amorphous polymers are made of randomly packed covalent chains that generate abundant free volume. Under bending, entanglements create more pockets of free volume, and it's in those pockets where an amorphous polymer will start to deform under load. That's because the chains are only held together by weak van der Waals forces, and they rupture easily. So this allows chain segments to rotate and slide. And then the molecular mobility produces visible deflection at low stress, and it increases steadily, reflecting the material's very low elastic modulus. Our takeaway here is that the weak van der Waals bonds and variable free volume don't really provide much resistance to deformation, and that's reflected in a super low elastic modulus. So let's talk about that elastic modulus. Basically, you give a material some stress and you see how much it fights back. It's the material's resistance to elastic deformation, the ratio of an applied stress and the resultant strain. We'll talk about high and low elastic moduli in a second. So here's a bar chart of stiffness values for different materials. This comes from Wiley's Materials Science and Engineering textbook. But because we're just looking at steel and PVC, I'll simplify it a bit. Remember how a crystalline solid like metal takes a lot of stress before it starts to deform, meaning high stress and low strain? That's a high elastic modulus. The atomic bonds strongly resist separations, and the atoms return to original positions with minimal displacement. On the opposite end, if you got high stress and high strain, that's a low elastic modulus. There's weaker intermolecular forces that yield more readily, and the structure deforms substantially under the same load. But what does all this mean? It means different materials will have different deflections. So beam deflections, or in this case, cylindrical rod deflection, is the amount of lateral deflection in a structural element, like a clothing rod given a uniform load. You can calculate the deflection at any point along its length. But critically, because of mathy stuff, deflection is inversely proportional to elastic modulus. So what does that mean? Well, let's put it all together. Atomic structure dictates elastic modulus. And that elastic modulus, being inversely proportional to beam deflection, helps you determine how much deflection you'll actually see. So anyway, how does this help me solve my problem? Math. It's the math. It literally just doesn't lie. So my problem is that I've got 62 pounds of uniform load across 31 inches. This equates to 2 pounds of force per inch of span. Now, as you might have guessed from the picture, I'm not using steel conduit as my clothing rod. I'm just using electrical conduit, just PVC. Now, polymers, like PVC, have that amorphous structure. Remember what our takeaway was about these structures? They have weak bonds and lots of free space. So this easily entangled network has minimal deformation resistance. So as stress is applied, the material experiences a lot of strain, so much so that its elastic modulus is less than 1. Check out that ratio. That means that as soon as you put, say, 62 pounds of clothes on 31 inches of span, you're going to see deflection, just like you see here. And remember, we can calculate deflection at any point given this information and known material properties. So what does that give us? Well, given that 62-pound load, these are the deflections that would be seen by 1 3/4 inch clothing rods made from steel conduit, PVC plumbing pipe, and PVC electrical conduit. The yellow and orange are 1-inch PVC pipes, and the green and blue are their 3/4 inch relatives. Which one am I using right now? This one. And that deflection calculation is pretty darn close to what I'm seeing in that picture. But I would like to draw your attention to these dashed lines here. Those are the calcs for steel. So why are those lines so high in the graph? Steel has the crystalline structure. Our takeaway there was that steel's strong metallic bonds are in an ordered lattice. So dislocations require significant stress in order to experience any deformation. That high resistance means it has a high elastic modulus. Comparatively, look at that ratio of stress to strain. Where PVC saw 3 to 5, steel is at 30 to 1. Meaning it takes a whole heck of a lot of stress to make it respond in any significant way. Now, once it does fail quickly. But remember where those dashed lines were in the graph? Here, let me zoom in on them a little bit. These are the deflections for the 1 3/4 inch steel conduit, given those 62 pounds. And these are their failure points. Not only does steel just barely deflect at the weights I'll be applying, it can withstand way more weight than I'll ever put on it. And it's not even cost prohibitive to buy steel conduit. So here, let's look at the overall deflection analysis I did and my subsequent embarrassment. This graph has all 3 materials at both 1 3/4 inch diameters. And this is what I'm currently using, 1-inch PVC electrical conduit. Remember that yellow dashed line is the current deflection of 62 pounds. I'm halfway to failure, and that's not even the heaviest set of hangers for that length of rod. Even worse, because some hangers have smaller diameter hooks, I bought 3/4 inch PVC conduit. Look at that failure point, 82 pounds, I'm almost there. I'll let you look at the other numbers in the center so you can see the sheer size of the delta between the 3 materials. Remember, the blue and purple up top there are steel. Tiny deflection, giant failure load, infinitely better for this specific application. Then the white PVC plumbing pipe are the bottom 2, the green and orange. Even those are a significant improvement over the actual things I bought to expand my closet. Why did I do that? I don't know. It's what I used originally? Maybe it's because I didn't have the bandwidth to think about it until I was forced to, with some project, in a class. Yeah, that sounds more like it. That said, this is a fun way to literally quantify how colossally dumb it was to buy electrical conduit instead of steel conduit for my clothing rods. So I guess I'm off to Home Depot to do my exchange. Thanks for tolerating my rants, and you're welcome for giving you the best idea for your next home project. Let me know how it goes. Bye.